Good afternoon, or good morning or night if you are attending from somewhere else in the globe. Excuse us for this delay. We are 5 minutes late. We had some technical issues before starting the session. Welcome to this session on meteorology and environment. My name is Xavier Prats. I'm an assistant professor and principal investigator at the UPC, Technical University of Catalonia, and I will be chairing this session today. We have 3 papers, and then after the papers, we have some poster teasers. So we'll have 2 papers first, then a small break to synchronize this session with the session that is going in parallel on safety. Okay. And after the 2 papers and this break, we'll have the 3rd paper and the poster teasers. So let's just start with our first presentation. Yeah, these are the 3 speakers that we have, and the first presentation will be given by Dr. Antonio Parodi. Dr. Parodi, he's a research director at the CIMA Research Foundation. He's an expert in a statistical analysis of extreme events and in atmospheric modeling over high performance and cloud computing facilities. We had some technical issues. No, you have to share the screen now. Matthias, yeah, exactly. So you are sharing the screen. This is the title of his presentation: How can Synoptica support ATM and ATC during severe weather events? So Antonio, the floor is yours.
Okay, good. I hope that you can hear me clearly. Shall I share also my screen? Sorry, my video, or shall I go directly only with the voice? Probably it's better to stop the video so the bandwidth is better.
Yeah,
so what I'm going to present briefly are the Can you hear me?
We hear you, yes.
Okay, good. So the presentation that I'm going to discuss briefly today is related to the to Horizon 2020 project. Was titled is Synoptica, and the leading question of this project, which is involving several European institutions like CIMA Foundation, DLR, Austrocontrol, University of Padova, University of Barcelona, and an SME from Italy, GRED, is basically to understand if this project can provide any good support for air traffic management and air traffic control activities during severe events. If you can move to the next slide. Thank you. The motivation for the Synoptica project is clearly coming from the fact that severe weather events may impact very seriously air traffic management and air traffic control activities. And along these lines, the prediction of very rapidly developing thunderstorm occurring over small and localized areas is a very big scientific challenge. Those events are usually characterized by the production of very huge amount of rainfall over a very short duration of time, high lightning activity, strong winds, and also large hail size. The 2 pictures that we have introduced with the help of Riccardo Biondi from UNPD in this presentation are really testifying to different scenarios, proving the words that I just spent. The one on the right is a specific Synoptica case study, and it is referring to a major hailstorm that took place on 11 May 2019 on Milano Malpensa area, where you have the impression that the full airport area is covered by snow while it was a major hailstorm. And the images on the left-hand side are conversely related to another event occurred more recently, this last summer, early July, when a flight from Air Emirates from Malpensa to New York was struck during the is basically takeoff and early routing phase by a major hailstorm, deeply affecting the cockpit and also the engine areas, at the point that the airplane had to come back to the airport. So it is clear that this phenomena may affect the flight safety, both when the airplane have to fly through those structures or nearby. And the overall idea of this project is to put together competencies from the meteorological community together with competencies from the air traffic management and ATC communities to try to provide better predictions. So what, if you can move to the next slide, please. What basically the project is aiming to do is to have a twofold approach to the problem. On one side, we want to exploit as many as possible observational data into the forecasting process. And we are speaking about radar data, like reflectivity radar data, GNSS data, which are very useful to know about the overall integrated water vapor content into the atmosphere, weather stations data in terms, for example, of temperature measurements or wind, lightning data, and GNSS raw data. And the idea is to collect those data for a certain number of case studies and to use those data as an ingredient for data simulation into a very high resolution WRF model. The study region that we have selected, if you can move to the next slide, the number 4, is referring to the if you can move to the next slide. Okay. If you click many times, you will see different images popping up. Okay, thank you. The event basic, the case studies that we did select into the projects are case studies which are referring to the Italian area. The reason why there is still one, if you click once more, there is also the Palermo case. The reason why is that in this way we could have, not the previous slide, we could have better access to observational data. And all those case studies are in one way or the other related to summer case studies, deeply convective in natures. Most of them are located in northern Italy, and we have to do with the Milano Malpensa case studies in May 2019, when a squall line affected the Milano airport, and you saw before the pictures of the airport in that day. Then we have other two cases, both occurring again in that summer, one over the Venice Marco Polo Airport, which occurred the 7th July 2019, which was a very deep, intense precipitation, mainly thunderstorm in nature, associated with very strong wind gust. We had further another convective event on the 6th August 2019, and this event was again heavy precipitation plus strong wind. And last but not least, an event occurred in southern Italy in July, 2 years ago, with a localized thunderstorm and very high amount of rainfall occurred in short time. What we are doing in the project is basically to use the WRF model, including the simulation, to try to tackle the prediction of those events at temporal spatial scales useful for ATM and ATC. If you can move next slide. Okay, this is basically an example of model output. It is referring to the specific case of the Malpensa event. You see on the upper left of this slide a maximum vertical integrated liquid water image related to the most intense phase of the event, where you see very high values of liquid water content in reddish color over Malpensa airport. And you see on the left lower corner 4 different maps showing the results in the most intense phase of the event of 4 different experiments. One assimilating radar data, RDR, one assimilating radar data plus GNSS, one assimilating radar data plus weather stations, in particular temperature data, and last but not least, radar plus lightning. What we did, beside a visual inspection of results already suggesting that probably the simulation with radar plus lightning data was the best performing, we also proved to do the object validation for the case studies. And basically what we did was basically to use a technique which is very well known into the WRF community, which is to compare objects in the predicted and observed field and to search for objective evaluation of the agreement. And if you see, basically we did such an evaluation using the centroid distance in the table, the observed areas, the one observed versus the one predicted, the degree of overlapping between the structures, and an overall measure of agreements with the interest function. All in all, what it is clear is that the simulation in this case, including radar plus lightning assimilation, is the one providing the best match, because the centroid distance is in the order of 40 kilometers. And also, at least partially, if you check the lower right image, the overlapping between the predicted and the observed structure is rather good. Still, there is room for improvement, because if you judge the VIL map on the lower right corner, you see that the simulation using radar plus lighting assimilation is providing a convective area larger than the one observed. So certainly there is a signal significant, but also a certain degree of false alarm. If you can move to the next slide, please. Thank you. The Synoptica project is not only about the weather prediction, but is also strongly involved in the role of the ATM community. And in this respect, what we did in the project was to collect the actual flight trajectories for that event when the airport was also closed before because of the hailstorm, with the idea of integrating into an extended AMAM logic the WRF prediction provided by the project with the trajectories diverted during the case studies. If you look at that image, you see a quite complex pattern of trajectories during the most intense part of the event. And you see also that at a certain point, basically the the travel time against the touchdown time become very very high, because this was due to the fact that the airplane had very significant trouble in getting to the land, to the point that the airport was closed. You can move to the next slide. The overall idea is basically to go with integration of the model output with Aman in order basically to put on the same side of the problem an improved weather prediction with a more accurate management of the ATM and ATC phases. If you go next. Okay. This is more or less all. I am ready to take questions, if any, from the audience, and thank you for your attention.
Thank you very much, Antonio. Thanks for the presentation. Thank you, Matthias, for managing the slides. Okay, it's time for questions. I would like to remind, I guess, that everybody's familiar already with the procedures, but I would like to remind to all our attendees that we should use the Q&A chat that is in WOMA. So, and I will take those questions as long as you share them in the Q&A chat. In the meantime, I would like to clarify something, Antonio. In one of your slides, you were referring you were referring to GNSS raw data. What is that exactly? It's raw. You mean the pseudo range, or it's something, or it's raw? RAW. I didn't understand exactly what do you mean.
Basically, sorry, I was not clear enough and good enough. There is also online Riccardo Biondi, who is a colleague from University of Padua, who is really expert in this field. Basically, GNSS raw is a specific family of radio occultation data, which is of GNSS data, which is related to radio occultation. And in principle, they are providing profiles of atmospheres, which can be useful for constraining the model. The difference is that with the classical GNSS data, you have simply an integral information. It is a proxy for the total water vapor content along the column, while the radio occultation data are even more interesting because they are helping us to get profiles of the atmosphere. But I don't know if Riccardo is willing to add anything specific about this point.
For me, it's okay. Just that I didn't know the acronym, so now I see it's radio occultation, so it's okay for me. Thank you. We have a question now in the Q&A. I don't know, Antonio, if you can see the questions. I will
yes,
read
I read it. If it is the one, what type of convective weather information are now consumed by Aman system? Do they use weather polygons to predict the future trajectories of arriving flights? Well, this is a very interesting question because it is deeply related to the overall synoptic approach, in the sense that when we prepared the proposal and we submitted it, it was clear that at this point in time, the amount of weather information available for air traffic managers, people, or air traffic controllers was mostly related to synoptic scale weather products provided by global circulation models like ECMWF or GFS, or products from local weather radar data in nowcasting mode. And what was very clear was that at this point in time, there are not available nowcasting products combining high resolution weather products enriched by data simulation with nowcasting radar approach. What we agree with and we decided also after a survey with different air traffic management people was that we have to pass to the extended AMAN framework polygons identifying in principle no flying zone. So a zone that for whatever reasons, mostly for very deep convection activity, have to be avoided by the flight. So at the end of the day, what we plan to do, and this is the last phase of the project, is to produce out of our weather forecast very synthetic information in terms of polygons identifying non-flying zone, either in terms of high values of liquid water content or high value of reflectivity, and basically to use them in order to have a tactical approach to the air traffic management and air traffic control activities.
Okay, thank you very much. We have a couple of 3 questions actually now. Let's start first with a question from Sebastian, Nick from Eurocontrol. He's reporting his experience in nowcasts, saying that the pilots often report borders of the cells that are different from what is nowcasted. So do you have any idea what we could do to improve this?
I hope that I got properly the question. Let's see. What we did realize during the project lifetime is that even using a methodological model enriched by a very large set of observational data, still the weather forecast of the model not necessarily is in great agreement with observations, in the sense that those events are very hardly predictable and both in space and time. So the strategy that we have in mind in the project is basically the following. The idea is to use a methodological model enriched by the observations that I did mention during the speech, in a rapid update cycle mode every 3 hours for the next 9 hours forecast time, to have an extended view of the possible convective events at the AMAN scale, while to rely on radar nowcasting products in order to have the prediction for the next, let's say, 30 to 45 minutes. In this way, we hope that the weather model with data simulation can give an overview of the situation in the next few hours with good accuracy, while for more precise prediction, the radar nowcasting is giving the near real time, the very near real time situation. In this way, in our experiments, we saw that the radar nowcasting decreased significantly the risk of false alarm or mismatch between actual observed structure and the one nowcasted. But Synoptica is a research project, so we have to perform more case studies, more experiments to consolidate the findings.
Okay, a couple of questions from Michel Travierso. First one is if he's asking if you have any experience with Rasp, the set of libraries developed for the gliding community, and if you could compare with them.
Do you have any experience with Rasp? No, I heard about it, but I don't have any direct experience. But I think that maybe it could be nice later to discuss with Michele about this opportunity, in the sense that it can be a nice extension probably to explore. But I have to admit that I don't have a direct knowledge. Sorry for that.
Okay. And one last minute for the last question, also from Michelle. how high can the resolution be before the accuracy will not longer improve? You can say something about the accuracy of your models.
If we speak about the meteorological model enriched by data simulation, we decided to stay around 2 kilometers grid spacing, which is basically barely cloud resolving grid spacing. If we go above it, we are entering into a cloud permitting grid spacing, which is less accurate and which is basically approaching the region where you have to adopt convective parameterization for forecast. And in this respect, the performance are degrading a lot. Probably for an operational framework, it could be possible to be more aggressive with grid spacing, not pretending anymore how we did in the Synoptica project to have a very large domain of forecast covering the entire Italy, but zooming down basically over specific airports. For example, I am aware that in the International Hong Kong Airport, we are running a very deeply resolved WRF model at grid spacing in the order of 500 meters in large edge simulation mode, but just focused on that airport. So in some sense, in my opinion, the kilometric scale or a few kilometers is basically the limit. Above it, it doesn't make any more sense in terms of predictive capability. The lower bound is limited by the scope. So if we want to focus just on a smaller region, we can be probably more aggressive but still delivering the predictions in time, because running those models is very time consuming and you have to enter into the business of petascale machine with computing with cores in the order between 500 up to 1000 in order to be capable to run a model in time for the ATM and ATC activities.
Okay, thank you very much, Antonio, for your presentation and for all your answers. Thank you also for the attendees and their questions. So it's time now to move to our second speaker, who is thank you very much. Who is Federica Castino, with the paper Seasonal Variability of Aircraft Trajectories, Reducing NOx Climate Impacts Under a Multitude of Weather Patterns. Ms. Castino is a PhD candidate in the section of aircraft noise and climate effects in the Faculty of Aerospace Engineering at TU Delft. Her PhD focuses on the optimization of aircraft trajectories in order to reduce the climate impact of aviation, which I see it's pretty much related with this paper, right? So Federica, the floor is yours, and you should share your screen if I'm not wrong, right?
Yes, good afternoon, everyone. Thank you, Professor, for introducing me. My name is Padeka Castillo. I'm a PhD candidate at TU Delft, and with my research, I contribute to the FlyITM4E project, in which TU Delft collaborates with DLR, University Carlos III of Madrid, and TU Hamburg. So today I'm going to present you our results on the seasonal variability of aircraft trajectories, reducing NOx climate impacts under a multitude of weather patterns. So in this first figure, you can see a summary of the different components of aviation climate impact and their relative radiative forcing terms. So you can see that aviation climate impact is due to both CO2 and non-CO2 effects, which include NOx emissions, water vapor, and formation of contrails. In particular, with the impact of NOx emissions, we have warming effects due to the perturbation of ozone concentrations and cooling effects due to the reduction in the concentration of methane, with a net effect that is warming, since the fast perturbation on ozone is dominating. And with non-CO2 effects, we know that these are highly dependent on the background atmospheric conditions, and therefore on the time and location of emission. And as a result, we have the potential of mitigating the climate impact of aviation by optimizing the aircraft trajectories. And this fact has been highlighted by previous projects. For example, in this figure, we have the results of the React4C project, in which the transatlantic air traffic was optimized with respect to the costs and the climate impact. And we can see that even 50% of the climate impact can be reduced with an increasing cost of 15%. But what is interesting is that already a 25% reduction in the climate impact can be achieved with only 0.5 increase in the operational costs. And subsequently, the ATM4E project found that for the European air traffic, 80% of the overall climate impact mitigation potential can already be achieved, modifying 25% of the considered routes. However, these studies selected a few representative weather situations. So in our study, we want to enhance the understanding of the relation between NOx climate impacts and routing strategies, considering a large number of weather patterns. And in particular, we focus on the effects on the routes if we optimize the trajectories with respect to the climate impact of their NOx emissions. And we also look at the seasonal variability of the properties of the optimal trajectories, which are caused by the underlying natural atmospheric variability. And this is an initial step towards one of the objectives of the ATM4E project, which is to identify trajectories leading to a significant reduction of aviation climate impact while leaving the economic costs nearly unchanged. So to take into account the atmospheric natural variability, we conduct long-term simulations with the atmospheric chemistry model AMAC. And to estimate the flight climate impact, we use a set of prototype algorithmic climate change functions, also called ACCFs, which take as arguments the atmospheric conditions simulated by AMAC. So for example, for the NOx climate impact on ozone, we take as input fields the atmospheric temperature and the geopotential, and we calculate the values of the ACCF, which are then multiplied by the amount of emitted NOx to obtain the climate impact of the emission, which is measured as the average temperature response over a time horizon of 20 years, so also ATR20. And here on the right, you can see an example of the ACCF values for December 1st, 2015. And you can see for both the impacts of ozone and methane, moving towards the pole, we have a reduction of the average temperature response. To optimize the aircraft trajectories, we use the Airchop model, which is coupled with AMAC, and uses a genetic algorithm, ARMOGA, to optimize the trajectory. And you can see the definition of the trajectory in this figure. We have 5 control points in the vertical profile and 3 control points on the surface of the Earth to define the B-spline curve representing the trajectory. Then several optimization strategies are available, for example, to minimize flight time, fuel use, simple operating costs, or the climate impact. So in this slide, we summarize the simulation setup that we use in our simulations. We conduct simulations of the duration of 1 year, and we optimize 85 flights in the European airspace. So you can see the location of the origin-destination pairs in this figure. And for each OD, we assign 1 or more departure times, which are repeated on every simulation day. And we compare 2 optimization strategies so that we have NOx climate optimal trajectories, minimizing the climate impact of NOx given by the sum of the ozone and methane effects, and cost optimal trajectories, which minimize the simple operating costs, or SOC, which are calculated as the sum of flight time and fuel use. So now we look at the results of our simulations. In this figure, we can compare cost optimal trajectories in red and NOx climate optimal trajectories in green. These are horizontal paths that are averaged over the winter months. And we can see that in general, we have a northward shift of the aircraft location. And this can be explained by looking at the annual zonal mean ACCS of NOx ozone. In fact, we can see that the warming effects from ozone are reduced, moving to higher latitudes. And for other seasons, we find a similar behavior, but the effects have lower magnitude, as we will see later. But now we look at the seasonal mean flight profiles. So we can now again see the cost optimal trajectories in red and the NOx climate optimal trajectories in green. And we can see that the NOx climate optimal trajectories tend to fly at lower altitudes than the cost optimal ones. And also we have a very strong dependency on the latitude. In fact, when we move towards higher latitudes, the flight altitude reduction is larger. And in this, we see a relation with the tropopause height. In fact, this height also reduces towards higher latitudes. And this is explained by the fact that at the tropopause, we have a sharp increase in the NOx climate impact due to the fact that the residence time of ozone is larger in the stratosphere. And again, looking at the annual zonal mean, we see indeed that warming effects of ozone are lower at lower altitudes, and that the gradients are also higher at higher latitudes. So since we perform 1-year simulations, we can also look at the evolution in time of the properties of the optimal trajectories. And in the upper panel, we have a comparison of the flight altitude evolution in time of cost optimal and NOx optimal trajectories. And we can see that cost optimal trajectories have almost a constant flight altitude throughout the year, with a very small variability among the different flights that we considered, while the variability is larger for NOx climate optimal trajectories, and they are also affected by a very strong seasonal cycle. In fact, the reduction in cruise altitude is smaller during the summer, and this can be explained considering, for example, that the elevation of the average height of the tropopause during the summer months. And also, as you will see in the next slide, that there is a lower mitigation potential in this period. The same seasonality is followed by the relative change in fuel time, flight time, fuel use, flight time, and SOC. And in fact, the fuel increase is driven by the increase in aerodynamic drag that is caused by flying at lower altitudes. And so we can also see that there is a larger variability in flight time during winter and spring. So now we can look at the changes in the NOx climate impact. And in this figure, we have the relative change in NOx climate impact using as reference the yearly mean NOx climate impact of cost optimal trajectories. So what we can see is that indeed, using NOx climate optimal trajectories, we can successfully reduce the aviation climate impact from NOx emissions. However, the mitigation potential is affected by a strong seasonal cycle, and the larger mitigation potential is found in winter and spring. And the interpretation for this result is that in winter, the jet stream is stronger and located further south over the European airspace. Therefore, we have larger vertical and latitudinal gradients in temperature and jet potential, which are the input fields for our optimization function. And here we can look separately to the two effects from NOx emissions. So we can see that in the upper panel, the NOx ozone climate impact reaches a maximum in summer, and this is due to a higher photochemical activity. And this is found for both optimization strategies. And you can also see how there's almost no potential to reduce this factor optimizing the aircraft trajectories. While for methane, we can see that the cooling effects are always enhanced throughout the year, but the reduction again is smaller during the summer months. So to conclude, in our study, we were able to use the air traffic simulator Airchop coupled with an atmospheric chemistry model, AMAC, in order to analyze and compare the different routing strategies under the atmospheric conditions computing during 1 year of simulation, so under a very large number of possible weather conditions. And we found that the NOx climate optimal trajectories are flying at lower altitudes, and they're also affected by larger temporal and latitudinal dependencies than cost optimal trajectories. And most importantly, we found that the mitigation potential of NOx climate impact is affected by a very strong seasonal cycle, and it is larger in winter and spring. So in my last slide, I'm going to present the next steps of our research. Firstly, we want to note that we employ in this study a set of prototype algorithmic climate change functions, and ongoing research is currently addressing several aspects in order to extend our simulations. Firstly, we want to take into account all the main components of aviation climate impact, so both CO2 and non-CO2 effects, including NOx, but also water vapor and control zeros. And then, as I stated in one of the first slides, the main objective is to identify trajectories leading to a significant reduction of aviation climate impact, while leaving the costs nearly unchanged. And lastly, we also want to include uncertainty ranges to the best estimates of the aviation climate impact and the properties of optimized trajectories. So I include in this last slide some useful references and the link to the project webpage. And with this, I conclude my presentation. Thank you for your attention.
Thank you very much. Thank you very much, Federica, for this presentation. We have 2 questions. Yeah, well, one question from Sebastian. I guess you can see the Q&A. He's asking for trade-off trajectories. We understand that you're optimizing for NOx, but then because of that, the trajectory will not be CO2 optimal. Do you have any info on which flight levels could be overall optimal for both NOx and CO2? So having a kind of trade-off trajectory.
Yeah, thank you for this question. Indeed, there's a trade-off between the CO2 emissions and the climate impact of NOx. So what we want to do indeed is to create an objective function that then can take into account both effects and then consider the possible trade-offs. So to do that, at the moment, we are really considering the different efficacies of the impacts in order to merge all the different components of aviation climate impact into a single objective function for the optimization model. So this is the end results.
Okay, thank you very much. Any other question? Remember to use the Q&A chat to post your questions. No questions. In the meantime, I have a couple of questions for you. You show that there is a strong dependency on the latitude. I understood it's for the troposphere, the change in the troposphere altitude, right? That's why you don't observe something similar as a function of the longitude. Is that right?
Yeah, exactly. And indeed, if we look at the distribution of the routes on our flight plan, you can see that if we observe, as we described in the paper, a slight dependency on longitude is only due to the distribution of the routes over Europe, so that, for example, we can see that for low longitude, we also have low latitudes. So this is an artifact of our selected flight plan. But indeed, if we look at the objective function that we are used, the dominant dependencies on latitude.
Okay. And which aircraft type did you use for those experiments you are showing? Or it's different aircraft types, you focus on only one aircraft type?
Yeah, we focused on, yeah, sorry, I didn't point that out. We use A330 aircraft models, and yeah, the Airchop model is currently configured for this aircraft type, but yeah, several other options can be taken into account, changing the model parameterizations.
And why did you choose the A330 for such, I would say, short or domestic flights in Europe?
Yeah,
or just
indeed, this is because the model is currently configured for this aircraft type, but yeah, we are generalizing the model so that the user can select a different aircraft type depending on the yeah, the region considered.
Okay, we have another question from Sebastian. He says that cirrus and water, excuse me, are quite difficult. So maybe a first step could be to consider just NOx and CO2. Do you have such information on CO2 as well?
Yeah, indeed, it's correct that especially control cirrus and water vapor have a very large dependency on the atmospheric background, and the uncertainty can be much larger than for the NOx climate impact. Yeah, but control cirrus can also, as maybe I can show the first slide. Yeah, like all the factors can.
Excuse me, that the CO2 should be easy to compute, right? Because it's directly proportional to fuel consumption. So it's, I understand that this question is, that you have very comprehensive models in cirrus and water and so on, but then CO2, that is just easy to compute from fuel optimal. It seems that you are not showing the results. I understand the question like this, yeah. I think.
Yeah. If that is maybe clear from the paper, and indeed, it's the struggle at the moment comparing different contributions is considering the efficacy of the different terms, so that to understand what is the response over a time of 20 years of these short-term responses compared to the CO2. Yeah, which is less dependent on time and location.
Mm-hmm. Any other question from the audience? I understand you are using B splines for the trajectory optimization. So does it mean you are not modeling your trajectories, that you are not modeling a constant altitude in cruise, right? So I understand that the aircraft is continuously climbing or descending, or can you impose this constraint in the optimization and allow for constant cruise altitudes, which is the operational way of flying, let's say, at least nowadays?
Yeah, that can be done. At the moment, we are using two constraints in the model. So lower and upper bound, but this can be set to force a constant value in altitude to just look at the horizontal changes in the routes. But in these studies, we also wanted to understand what was the optimal flight altitude in case we want to reduce, to minimize the NOx climate impact.
And related with this, do you think that 3 control points is enough? Did you explore more control points in the optimization? I understand that the more control points, the more computational time, but do you have an idea on the sensitivity of the number of control points you use?
Yeah, in this, there's a trade-off between the number of design variables and the computational time. But previous studies understood that with this configuration, we can obtain a convergence of the optimal results. But yeah, indeed, there's also the plan to use, for example, different definition of the geometry of the trajectory to understand how that is affected. But as a number of design variables, this is, let's say, the optimal for the present geometry definition.
Okay, thank you very much. And the last question, this is from Carol Gotts. Yeah, the question is about how fast is the algorithm. So it's pretty much related with your last answer. So what is the computational time? If you can give some figures on that. And if you think it could be operationally possible to use your work in real operations.
Yeah, regarding the first question, for example, simulation of the duration of 1 year takes about 1 week to be completed. So that is a good compromise currently. And talking about operational use, the idea is to explore what are the conditions that could lead to a particularly high or dangerous situations, or particularly eco-efficient conditions, so that we can detect them and include them in the air traffic management. So to detect regions where the atmospheric conditions have a correlation with high danger or high potential.
So I understand you said 1 week for the experiment you run, but for one trajectory, more or less, how long it takes to optimize this trajectory?
For one trajectory, I would say like half an hour for 1 day of simulation. So it's it's mainly combining the atmospheric the computation of the atmospheric conditions with the optimizer.
Okay, so thank you very much. Thank you for your presentation and for answering all the questions. So we have now just a 3-minute break, just a small comfort break, in order to be synchronized with the parallel session, okay, just in case that somebody is popping up at 4 p.m. So we'll just wait for 3 minutes, okay? And at 4 p.m. sharp, we will start with the third presentation. So see you in 2 minutes, actually. Okay, so that was a very short break. Welcome back. And for those just joining, my name is Xavier Prats. I'm chairing this session in meteorology and environment. And we have now our last paper. We have one paper and then some teasers, poster teasers. So the next speaker is Dr. Emmanuel Sunil with the presentation entitled METSIS, Hyperlocal Wind Nowcasting for U Space. Dr. Sunil is a researcher at the ATM and Airports Department of NLR, the Netherlands Aerospace Center, where he works exclusively on drone airspace integration projects for both U-Space and IFR remotely pilot aircraft systems. So, Emmanuel, the floor is yours.
Thank you very much, Xavier. By the way, is my screen visible?
It is, and we can hear you out and loud.
Okay, thank you. Well, thank you, everyone, and good afternoon, everyone. Thank you for joining this presentation. As was just mentioned, my name is Emmanuel Sunil. I work at NLR, and in this presentation, I'll talk to you about the METSIS, or Meteo Sensors in the Sky project, where we essentially try to look at the feasibility of using drones as an aerial sensor network for wind nowcasting for U-Space applications. So this presentation will be divided into four main parts. First, I'll talk to you a little bit about the background of this project and why we are doing it. Then I will talk about the experimental validation. So in this study, we did wind tunnel testing and flight tests. So I'll talk to you a little bit about the design of those experiments. In the third part, I'll talk about the results, of course, and only a small part of the results. If you're very interested after this presentation, I invite you to read the full paper. And finally, I'll end with the main conclusions of the study. So let me get started with a little bit about the background. So what exactly is METSIS and why do we need it? Well, at this point, everybody's familiar with small drones, and it's because small drones have a lot of applications and they've become, as a result, very, very popular. So we're talking about things like package delivery, filming, disaster management, and it seems every day they're coming up with more and more applications for small drones. But one very important factor to consider is that small drones are very lightweight, and they are also, as a result, quite vulnerable to the wind, especially at low altitudes, because the wind is quite unpredictable there. So something needs to be done about this. Now, luckily, U-Space, which is the European ATM system equivalent for drones, has thought about this. And there is a proposal for something called the U-Space Weather Information Service, which is supposed to present drone operators with all the relevant weather information, including hyperlocal weather information that is required for drone flights. Now, the METSIS project aims to look at hyperlocal information, particularly focusing on the wind component. So here we're really looking at the possibility of using drones as an aerial sensor network for low altitude hyperlocal wind nowcasting. Now, this is a very small project. We only have two partners, NLR and AirHub, but we're not very familiar with the weather aspects. So we included in our project some experts from the KNMI and TU Delft that are much more familiar with weather aspects. And as I mentioned before, it's funded through the SESAR Engage knowledge transfer network. So the METSIS concept, well, it actually consists of 3 steps. In the first step, the drones that are already flying around, they use wind sensors on board, or they infer the wind in other ways, and they measure that data and they downlink that data to a ground station. Let's call it the METSIS ground station. The METSIS ground station then aggregates all the data from the different drones and uses something called the Meteo particle model, which I will go into a little bit detail later. And it uses this model to estimate the wind field in that particular area. So in this graphical representation, you see the solid arrows are actually the measurements from the drones, and the dotted arrows are the estimate from the Meteo particle model. So the nice thing is that you have an estimate not just at the locations of the drones themselves, but also in the surrounding areas. And finally, in step 3, the ground station transmits this wind estimate for the area that you're looking at to all the drone operators. and they can use this information for various purposes. For example, to optimize their routes, taking into account the winds. So now this Meteo particle model, which is actually at the core of this METSIS project, was actually invented in TU Delft a couple of years back by one of my good colleagues, Junzi Sun. And it was actually demonstrated initially for high altitude air transport aircraft. So what happens here is you initially have the wind measurements from individual aircraft. And for each measurement, you generate a large number, thousands of imaginary particles that carry the information, the measured information, wind speed in this case. And these particles propagate in time, taking into account the wind speed and direction, but also a random walk factor as well. And finally, you reconstruct the wind using a predefined grid, let's say. And at each grid point, you look at all the particles nearby, and there is a sort of a way to reconstruct the wind based on the homogeneity of the particles at that particular grid location. And the nice thing about this method is that it also gives you a confidence interval for each estimate. And in the third GIF figure, you can see the green color. The more green it is, the more confident the estimate, because there are more data coming in from that location. So the objectives of the METSIS project was to look at the accuracy of this concept, especially in the presence of static obstacles at low altitudes, and then also to look at how to communicate this information to drone operators using a U-space system. And in this presentation, I'll really focus on the accuracy part, because that was, as NLR, our primary focus. Our collaborators, AirHub, really focused on the second topic. Now, in METSIS promises many benefits. First of all, it could be a very nice low-cost and real-time solution to the wind nowcasting problem, because the data is provided by the drones themselves. Now, this data could have many applications. For example, you could optimize drone trajectories with respect to the wind. And this is not only useful for safety, but it's also very important for efficiency, because a lot of these drones are battery powered. And if you have very strong wind fields, the range that you can fly is a lot less than what you would have without the wind. So it's very important to optimize your trajectories with respect to wind to be able to sometimes even just be able to do your mission. So that's also very useful. We're trying to make a tangible contribution to the U-Space Weather Information Service. But apart from drones and U-Space, this data could also have other applications. For example, at present, we don't have very high quality wind measurements within urban environments at low altitude. So this could be used as an additional input to national meteorological systems, but it could also be used for other things, such as, for example, when a helicopter wants to land on a ship, wind plays a very important role in that operation. And if you can use drones to get a better accurate wind field around the ship, that can really help the helicopter pilot. So there are many potential benefits to this METSIS concept. So the next part of the presentation, I'll talk about the experimental validation that we did. So as I mentioned before, we did a flight test at the NLR Drone Center. The drone center has a lot of facilities, including a runway, but also, more importantly, perhaps, its own airspace. So we can fly there without interfering with other traffic. In the project, we actually use 4 sensors and 4 drones and 4 sensors. And you get a feel for that from this picture. And in fact, this is the actual drone that we used. So it's all based on commercial off-the-shelf parts. We have a quadcopter drone, which had a maximum flight time of around 20 minutes. We used an ultrasonic wind sensor, and to prevent the propellers from interfering with the wind measurements too much, we separated them using a pole. Now, I'm not saying that the METSIS concept requires a dedicated wind sensor, because it would be quite difficult to fit such a sensor to every single drone that's flying. But for the purposes of this project, to look at our specific goals, this was the easiest and fastest way. And that's why we decided to go in this direction. But this is something I'll get back to towards the end of the presentation. So how do we measure accuracy? Well, we wanted to keep it rather simple. So what we did was we split our 4 drones into 2 categories. We used 3 of them to feed the actual METSIS network. We called these drones the measurement drones. And then we had 1 reference drone. And this reference drone would fly around, and we would compare the estimate from the MPM to the measurement from the reference drone. And the difference would be used as sort of an accuracy measurement. So in this way, we could simplify our experiment by just making 4 very similar drones. Now, because we're using the same drone for the reference measurement, we really have to be sure about the quality of our measurements. So for that reason, we performed a short wind tunnel test in one of our wind tunnels, where we considered various different wind tunnel speeds, different angles of attack, and also cases with and without the propellers rotating. And I'll get back to the results in the next part of the presentation. Now, for the actual flight test, we wanted to have several scenarios that could be compared with each other. So we decided to have a sort of a predefined topology for the different drones. So the measurement drones, they were positioned like an equilateral triangle, and the reference drone, it would move into different locations within this this triangle, numbered here from R1 to R3. Now, we had static scenarios where the drones were essentially hovering, but we also had dynamic moving scenarios, let's say, where the measurement drones would fly in a circular pattern, but the reference drone would always remain static. So to increase the quality of the reference drone measurement, essentially. We considered several different scenarios during our flight tests. So different altitudes, different distances between the drones, different drone speeds, and 2 different obstacles. The first one is a sort of a van and a trailer, and the second one is a row of trees near the runway that we had. So to give an impression about the experiment, I have this short video, and here you can see the dynamic conditions. So you can see the reference drone going to different locations within the triangle, and the measurement drones flying their circles. And of course, it's fast forwarded, so the real drones were not flying as fast as you saw in the video. Okay, so let's take a look at the results. So what's the kind of output that we can generate with this? So here on the left, you see a GIF with the output of the Meteo particle model. So here, each little graph is actually 1 slice of altitude, and the black arrows are actually the wind estimates from the MPM, and the green color depicts the confidence of the estimate. Now, in this particular run, the drones themselves were located at 10 meters altitude. Those are the red arrows, and that's why it's more green at this altitude, and it becomes less and less green as you go higher. For example, at 80 meters altitude, the estimate is pretty has less confidence than at 10 meters. Now, as I mentioned, we transmitted this data to Airhub, and they displayed this information on their drone operation center, which is a sort of a tool that they have to plan, log, and fly drone flights. So we transmitted the data to Airhub every 30 seconds using a technique called HTTP post, and the data was provided in a JSON format. And they could then, in real time, show the updated wind fields on their interface. And the interface also made it possible, for example, to use sliders to select which particular altitude you're interested in, but also sliders to only show wind estimates that meet a minimum confidence level. Some more quantitative results. So the wind tunnel data, the wind tunnel results for the anemometer. So here you have 3 box plots. Each one is for 1 wind tunnel speeds for 6 meters per second, 9 and 12 meters per second. On the x-axis, you have angle of attack, and you see 2 different types of box plots. The orange ones are when the propellers are off, and the blue ones are when the propellers are on. And here you see the dotted line, that's the actual wind tunnel speed. So for example, at 6 meters per second, the real wind in the wind tunnel is 6 meters per second, of course. And the box plot gives you an impression of what the sensor is actually measuring. And you can see that the sensor is somewhat close to the actual wind speed, but never that perfect. And there's clear effect of angle of attack. In fact, when you change the angle of attack from anything from 0, it starts to degrade rather quickly. And you also see that that when the propeller is on, the error is generally even higher, which indicates that the rotation of the propeller definitely has an influence on the measurements made by this particular anemometer. So it's important to keep that in mind when looking at the results of the flight tests. Now, the results of the flight tests themselves, I've sort of it's sort of aggregated in this figure. So you have the different obstacle types here. You have the static scenarios on top and the dynamic scenarios on bottom, and then the colors to indicate different parameters. So the blue one is about wind magnitude, and the other colors are related to wind direction in different planes. To give you a feeling about the accuracy, let's take a look at the World Meteorological Organization standard for anemometers. And the standard says that for wind speed, you should have an error that is 0.5 meters per second or lower for wind speeds less than 5 meters per second. And the wind direction should be plus or minus 5 degrees. So when you look at the blue bars, which is the wind speed, you see that we're almost meeting the standard, the WMO standard. So that's quite promising. Keeping in mind that the wind speeds during the experiment were actually quite low. We unfortunately did not select a good day for the flight tests. It was rather light breeze throughout the entire day. But keeping in mind these low wind speeds, the accuracy is not too bad. On the other hand, the wind direction is always quite far from the WMO standard. So if the standard is about 5 degrees, it says, and our this is the axis for the wind direction, and as you can see, the wind direction error is actually quite large. So we did some more investigations on this. We expected this to some degree because of the from the wind tunnel test, we knew that the wind sensor is not as accurate as advertised. However, this was worse than we expected. So we definitely took a second look at this. And so in these two graphs, what you see here on the x-axis is the average wind speed, and on the y-axis you see the errors in the vertical direction and the horizontal direction. And you can sort of see a trend that the errors really decrease as the wind speed increases. So this is a sort of a property of the wind sensor that we're using, is that at very low wind speeds, it tends to be less accurate. And if I go back to the wind tunnel experiment, you can also see that to be the case, that at the lower wind tunnel speeds, the accuracy is generally less, especially when the angle of attack increases. Now, in terms of effective obstacles, because it's also something that was important in our study. So in this graph here, you see the wind speed, the horizontal wind speed. The columns are the different obstacles. So the baseline condition has no obstacles. And then you have the trailer and the trees. And the different colors indicate the different distances between the drones. And of course, the rows indicates the different altitudes that we had during the experiment. The y-axis here is the error. And well, one very quick observation is that for the tree scenario, when you fly below the tree line, the average wind speed, which is shown here below each of the box plots, is significantly less, which makes a lot of sense, of course, because the trees are shielding the wind, and so the drones experience less wind below the tree line. But on the other hand, when you look at the error error box plots, they all seem to overlap, which is actually a good thing, which means that the obstacles don't really have a significant effect on the error of the that is being produced. So that's a pretty nice promising result. Now, in the actual paper, we look into many more aspects, such as the effect of drone motion, effect of number of drones, effect of random errors in the measurements. I invite you to read the paper to find out those results. But now I will go to the conclusions of the presentation. So very briefly, this concept was about using drones as a sort of a low-cost aerial sensor network for hyperlocal wind nowcasting, primarily for use-based applications. We tested it using 4 drones at the NLR Drone Center, and based on the results that we see, it looks like the concept is feasible, but it also looks like that the accuracy of the model needs to be improved, especially if you want to deploy this for real operations. So that leads me to the recommendations. So first of all, we had an experiment, a one-day experiment with a limited number of scenarios. So to gain a more to have a better feeling for the real accuracy of the concept, we need to do much more experiments, more scenarios over multiple experiment days, because we'd like to see different wind patterns, and then we can be more sure about the accuracy of the concept. Another thing that we want to definitely do in the future is to increase the scalability of this concept. As I mentioned at the beginning, we used wind anemometers in this project to simplify the experiment. However, it's quite unrealistic to fit these on every single drone. So it would be better if we could use indirect wind measurements methods that do not require this dedicated anemometer. For example, if we can measure ground speed and airspeed, then you can infer wind speed from there. For a quadcopter, you could also look at the rotation speeds of the different propellers and the target ground speed and the orientation of the drone to also infer the wind speed from those measurements. So these are indirect wind measurement techniques that could increase the scalability of the concept. We also want to increase the accuracy. For example, the underlying MPM model has many parameters, and it may be possible to do some online tuning of these parameters. For example, using something like a particle swarm optimization to rapidly tune these parameters. We also want to increase the utility of the method. So right now we are able to produce wind estimates, but I think for drone operators, it's also important to show them how to use these estimates to dynamically calculate wind optimized trajectories. So this is something that we also want to look into the future, so that the method has real value for drone operators. And these are all things that we are very much interested in looking in future projects, and we, especially as SESAR 3 is going to be, well, the calls for SESAR 3 are going to start very soon. So if you're interested in partnering with us on this very interesting project, well, please contact me and we can try to set something up. With that, I'd like to end this presentation. If you have any questions, yeah, please let me know.
Okay, thank you very much, Emmanuel. We have time for a few questions. It's a little bit late, but let's try to be quick. We have the first question from Carol Gotts. I think you answered it just 1 minute before. He was asking about the possibility to incorporate gyroscopic data with barometer data in order to calculate the wind.
Yes, so it's a very good question, because at the moment we are using these anemometers, but it would be better to use indirect wind measurement techniques that don't require dedicated sensors for that. So, for example, we're thinking about, for example, using a very simple pitot tube, which is a factor 100 cheaper than the wind sensor, to measure the true airspeed, We already know the ground speed from GPS, so then we can try to infer the wind speed. Another technique that we want to try is, of course, using the rotor speeds and the attitude of the drone to also infer the wind speed. So these are two techniques that we want to look at in future projects.
Okay. Thank you for the answer. Another question from Daniel Gonzalez. He's asking if the measurements are instantaneous or if you are averaging over temporal windows to reduce the variance of the measurements.
That's a very interesting question. It's a little bit of both. So in theory, the method is instantaneous. However, when you work with sensors, probably know that every once in a while they produce a very strange result and then very quickly recover to the correct value. So we do have a sort of a moving average filter used in the process to iron out those kind of strange, erroneous measurements. But in theory, it should be 100% instantaneous.
Thank you. And what would be the last question for today from Ender Setting? Can drone swarms with an alternative method, for example, machine learning, could improve the accuracy of those predictions? Or it would take too much time to process all the data in real time?
That's quite interesting as well. And I also tried to mention that towards the end. So this model that we are using, this MPM model, has quite a few parameters, around 10, 15 parameters. And something that we're thinking about is using machine learning techniques or maybe some kind of optimization techniques to rapidly optimize these parameters for the particular situation that the drone is encountering. So it is something that we are considering in the future. But indeed, it should be real time because the processing shouldn't take so long.
Any other question?
That it takes the data is not valid anymore.
Okay. Any other questions from the audience? If I may, I will ask a quick question from my side. You are using the MPM methodology, no? That was developed and was tested for high altitude aircraft, where the atmosphere is much more stable. So did you notice any challenge or any particularities to employ the same methodology when you try to estimate wind at such a low altitude?
Yes. So yeah. Indeed, the method was originally meant for higher altitudes where the wind is much more stable. So the MPM has a lot of parameters that you can use to make it update more fast, let's say. We also made some changes. For example, we added the vertical component of wind, which was not there before. So we added that because that's an important aspect towards when you talk about operations near the ground. We also looked at sort of particle ground interaction, a very simple way to keep the ground into consideration when you talk about the propagation of the particles.
Okay, thank you very much. So thanks again for the audience for the questions. And that's the last presentation for this session. So now we will have 3 poster teasers. And then that will conclude this session. So Matthias, whenever you want, you can launch the videos for the teasers. Yeah, perfect.
Hello everyone, this is Antonio Franco, and I'm here to encourage you to see what we have prepared to show the advances in FMPMed project. In a nutshell, FMPMed aims at providing the flow management position with an intuitive and interpretable probabilistic assessment of the impact of convective weather on the daily operations. During this first year, we have developed the computing infrastructure needed to perform the traffic analysis required to support the FMPs, namely the ensemble nowcast and a unified framework for trajectory prediction. Traffic analysis and FMP-MET concept assessment will be performed on the second year of the project. So I hope you enjoy the full-length video and the poster we have prepared for this 11th edition of the SESAR Innovation Days. Thank you for your attention.
Okay, so that's all. Thank you very much for the people preparing these teasers. So this concludes this session for today. Remember that we have at 5:10 p.m. CET the SESAR Innovation Days quiz. So in the meantime, I encourage you to visit the poster section on the WOVA webpage, and let's see you again, maybe in person in the future in another conference or in another meeting. So thank you again for all the attendees, and have a nice day. Bye bye.